Hello guys, welcome back to another lecture of electrostatics. In this lecture we are going to talk about Coulomb's law in vector form and equilibrium problems. So let's start with Coulomb's law in vector form. So let's say we have two charges q1 and q2 and they are separated by a distance say r, and we are being asked to write the force on q1 but in vector form. So how do we write it in vector form? We know the force, Coulomb's force F, we can write as K Q1 Q2 by R square. But, but this is only the magnitude part, right? Here force experienced by both 1 and 2, both are of same value K Q1 Q2 by R square. But what about the direction now? See, if both of them are of same sign, if both of them are positive or both of them are negative, then the force will be repulsive in nature. And if they are of opposite sign, then it will be in attractive nature, right? So if repulsion, let's say on q1 a repulsive force is being applied, so in that case the direction will be like this, and if q1 is being attracted, then the direction will be like this. In any case, always the direction will be along the line joining the two charges, right? So here, if we consider the sign in q1 and q2, during calculation of magnitude we only put the magnitude of q1 and q2 here. So in this case, if we write it in vector format, I can write this way, that force on charge 1 due to 2, force on charge 1, this is charge 1 here, force on this charge due to 2 will be in this direction, right? So the direction I will write it. First I will write the magnitude part here, K Q1 Q2 by R square. Now about the direction, I will write direction of 1, position of 1 with respect to 2. The direction vector I will write this way. So instead of vector format, I will write unit vector because the magnitude is already defined. So it will be unit vector, my mistake there. So it will be unit vector. So what does it mean? This F12 means force on 1 due to 2. And what about R12 means? This means position vector of 1 with respect to 2. So if the 2 points position vectors are given, we can also write the R12 vector this way. See, F12 I can write as K Q1 Q2 by the magnitude square, but the magnitude I am writing as R1 minus R2, this is magnitude square, and R12 unit vector I can write as R1 vector minus R2 vector by R1 vector minus R2 vector magnitude. So the final expression will come to be like this, F12 I can write as K Q1 Q2 by R1 vector minus R2 vector mod to the power cube into R1 vector minus R2 vector. So both this one and this one can be written. Here we have directly written it in vector format, but in this case, if the two positions of the two individual charges are given, we will use this format, but we have to mind it here, q1 and q2 must be put with sign. So here the concept is q1 and q2 must be with sign. So in this case, even if R12 vector, see R12 vector here, if I want to show position vector of 1 with respect to 2 will be this way. But if the forces are of attractive nature, let's say both are of opposite sign, q1 is negative, q2 is positive, or vice versa, in that case the force will be in opposite nature, right? So in that case the direction should be this way. If we have any one of the charge as negative, then anyway the vector will point in opposite direction. There will be a minus sign coming out, and automatically it will be pointing towards the negative direction. So we have to pay attention when we write Coulomb's law in vector format. We have to put q1 and q2 charge in vector form, sorry, q1 and q2 with sign. Now let's just take an example. Let's say we have two charges. Here we are given with q1, and here the charge q2 is there. The value of q1 is given as plus 3 into 10 to the power minus 4 coulomb, and value of q2 is given as plus 10 to the power minus 4 coulomb. They have said that position vector of q1 is, this is the coordinate is 2 comma 0 comma 5, let's say, and for q2 the coordinate is given as, let's say, 1 comma 2 comma 3, and say we are needed to calculate the force on q2, due to q1. This is being asked to us. Then how do we find it? See, we already have seen it, the force, electrostatic force F on 2 due to 1, we need to write it as k q1 q2 by r square into r of 2 with respect to 1 in that direction unit vector, right? So first let's find the r21 vector. What is r21? This will be position of 2 minus position of 1. But position of 2 is given as 1 comma 2 comma 3, and position of 1 as 2 comma 0 comma 5. So the vector form will be 1 minus 2 I cap plus 2 minus 0 j cap plus 3 minus 5 k cap. Hence our position vector comes to be minus I cap plus 2 j cap minus 2 k cap. Then the magnitude of r21 vector, this one's magnitude will be minus 1 square plus 2 square plus minus 2 square whole under root. So this will be for 9 root over of 9, which is 3. The distance between them we got as 3, and r2 minus r1 vector also we got. So the unit vector along r21, the unit vector is the vector minus I cap plus 2 j cap minus 2 k cap by magnitude of the vector. So now the force, if we need to calculate the force will be, say, F equals to K, which is 9 into 10 to the power 9, Q1 and Q2. Q1 and Q2 values are given as 3 into 10 to the power minus 4, and Q2 as 10 to the power minus 4. Both are positive signs, so we don't need to bother about the sign here. So K Q1 Q2 by R square, R is 3, so 3 square. Now the unit vector we need to write, which is minus 1 by 3 I cap plus 2 by 3 j cap minus 2 by 3 k cap. Now solving this will give us the final result. Now let's see how to deal with equilibrium problems. The first question here says, find the distance from 4q charge at which a point charge should be placed so that it remains in equilibrium. So we are given with two charge system 4q and 9q, and they are asking at what distance from 4q here, either on this side or anywhere somewhere, at which point, at which distance from 4q we should place a charge so that that third charge will be in equilibrium. Two charges are there, we need to place a third charge and it should be in equilibrium. So see, if we keep it anywhere else which is not on the line joining the two charges, in that case 4q and 9q both will either repel it or both will attract it. In any case, the two forces will not be in opposite direction to each other. So if it is a positive charge, 4q, due to 4q force will be this way, due to 9q force will be this way, so net charge will be away. And similarly, if it is a negative charge, 4q will pull it, 9q will pull it, so net force will be in this direction, it cannot be in equilibrium. So along the line joining, if we keep it somewhere in the middle, then due to 4q, let's say it pushes it, if it is a positive charge, 4q will push it, 9q will also push it, and the direction of these two forces are opposite to each other. So here there is a chance of balancing. Let's say we keep it somewhere outside the two charges. In that case, 4q will push and 9q will also push it. These two forces will be in the same direction, so they cannot cancel each other again. So we know that if the concept point here says, it says like this, if two end charges are of same nature, here we have two end charges and they are of same nature, then the equilibrium point will lie in between the two charges. So somewhere in between the two charges it will lie. So I am keeping it, a third charge I am assuming, which is q. I am keeping it at a distance x from 4q. Now we need to balance the net force on this q, right? So due to 4q, what will be the force? I am writing k 4q times q by x square. The distance is assumed to be x. And from this side the distance will be L minus x, right? So I am writing k 9q into q by L minus x square. So from here k, q and q gets cancelled. We get 4 by x square equal to 9 by L minus x square, and by cross multiplication we get 9 x square equals to 4 into L minus x square. Taking root over here, this 4 L minus x square root over gives us plus or minus 2. If we are taking root over on both sides, on any one side we need to write plus or minus sign, right? So solving it, we have two values of x as 2L by 5 and x as minus 2L. See, if we consider x as minus 2L, look, this distance which is L minus x, if we consider x to be negative, then net distance will be L plus, instead of x we will write 2L, right? Basically L minus of minus 2L, it will be L plus 2L, 3L distance from 9q charge. That means the point will lie somewhere here, because from 9q it is at 3L distance, and from 4q the distance is x equals to 2L. That's why it will lie outside, but outside point cannot be valid. Basically this solution gives us, as we are balancing the two forces, the mathematical equation doesn't know we are trying to take the direction opposite or same. This value gives us the data where the forces are of same value, but they are not of opposite sign. Here we already know from the concept point, we already know that the outside point will not be equilibrium point, even though two forces are same, but they will be in the same direction. This gives us the two forces magnitude is same, but direction is not opposite. X equals to 12 by 5 gives us both the magnitudes are same and the directions are opposite. So this x equals to 12 by 5 is our real answer here, because here it is actually equilibrium point. The two forces are of same magnitude and opposite direction. Again, at x equals to 12, the two forces will be of same magnitude, but the direction will not be opposite. Mathematically, when we are trying to solve it, this equation doesn't know we are trying to take the opposite directions, right? The two directions should be opposite, that we have assumed from our concept point already. The mathematical equation, we do not involve that minus sign here. Okay. So let's go to the next question. Here we are given with again two charges, minus 16q and 9q, and again the distance between them is given as L, and it is asking us find the coordinate of the point at which a point charge should be placed so that it remains in equilibrium. So again we need to keep a third charge, and that third charge will be in equilibrium. But in this case, see, if we assume the third charge to be placed somewhere in the middle, minus 16q, let's say this is a positive charge, then minus 16q will pull it towards itself, and 9q charge will try to push it. So if we keep the charge somewhere in the middle between the two charges, then the two forces will be in same direction. Similarly, if we assume a negative charge to be placed, then minus 16q will push it and 9q will try to pull it towards each other, towards itself. So in that case, these two forces again will be in same direction, they cannot cancel. So the point, even if we get a solution where the two forces are equal, but they won't be in opposite direction, so they cannot cancel each other. So where the point can lie? Now see here, we can choose a point here where 9q will try to, let's say we keep a positive charge here, 9q will push it, but 16q will try to pull it. Now the directions are opposite. Similarly, if we keep it here, let's say positive charge here, then 16q will pull it, but 9q will try to push it. Again, the two directions can be opposite to each other. So on the outside, we can find a point. Now the question comes, if we consider an outside point, then where? Will it be closer to 9q? Will it be closer to minus 16q? Or both can be the answer. Now see again, we will apply a little bit more logic here. Say I choose a point here near to 16q. So this distance will be x and this distance will be L plus x. So when we try to balance the net forces, K 16q by x square equals to K 9q into q by L plus x square. So from here 16 by x square equals to 9 by L plus x whole square. Look at this equation here. Here the numerator is more and the denominator is less. Comparing the two numerators, 16 is more than 9. And comparing the two denominators, x square is less than L plus x square. In that case, 16 by x square will always be a bigger number, because if numerator is more, see 16 by x square, here numerator is more, so the value tends to be on the higher side. Again, x square is lesser, if the denominator is smaller, again the fractions value increases. On the right side we have 9 by L plus x square. So comparing these two, this becomes smaller. Comparing these two denominators also, L plus x square in the denominator makes it even smaller. So they cannot balance. The two forces cannot be equal. Instead, if we choose a point here, then what happens? In this case, near to 9q, I have, let's say, distance x, and from minus 16q, the distance becomes L plus x. So in that case again, K 16q by L plus x square can be K 9q by x square. Now the equation becomes 16 by L plus x square equals to 9 by x square. See here, numerator is more, but denominator is also more. So there is a chance that these two ratio will be equal to these two ratio. Okay. So let's go to the solution here. Let's see it. From the question, the arrangement of charge is different. So let's just exchange the two charges here and we can continue with our normal solution then. I'm taking 9q here and 16q here. Okay. So let's continue with the solution now. Here I'm taking the x value nearer to the 9q charge. Now the force on this q due to 9q will be k 9q into q by x square, and due to 16q the force will be k 16q into q by L plus x square. If we equate them, again we get two values, x equals to 3L and x equals to minus 3L by 7. X equals to 3L gives us this point, but x equals to minus 3L by 7 gives us a point somewhere here. Again, this data tells us the forces are equal in magnitude, but the directions are also equal. So if both of the forces will be in same direction, they cannot cancel, right? So this point here, which corresponds to the answer minus 3L by 7, even if the two forces are same at this point, they are not of opposite nature. The direction is not opposite to each other. So here it is not technically an equilibrium point. The equilibrium point will be for x equals to 3L. So the concept here says, if the two end charges are of opposite nature, then the equilibrium point lies on the extended line joining the two charges. So we join the two charges and extend it beyond the two charges. In that case, the equilibrium point lies on the extended line and closer to the charge having smaller magnitude. Look here, 9q and minus 16q. If we see the magnitude, this is 9 and this is 16q, right? So the equilibrium point lies to the smaller magnitude charge here. It is nearer to 9q. Nearer to 16q, we cannot get equilibrium, because if the distance will be lesser, the force will be more. Again, the charge magnitude is more, hence the force will be further more. So this force and 9q, force due to 9q, they cannot balance each other anymore. I hope it is clear. Here the question says, it is the arrangement is similar to the first one, but now the question is bit different. Now here it says, find the distance from 4q charge, the third charge distance from 4q charge, at which a point charge should be placed, and its magnitude also we need to find, the magnitude of q in terms of capital Q, so that all three remain in equilibrium. We need to find the position, and we also need to find what is the magnitude of the charge, so that all three will be in equilibrium, all three of them. So to solve this kind of problem where they ask all the charges to be in equilibrium, our steps are as follows. First, to find the position of the third charge, we have to force balance on the third charge, which we have already done. In the first example here in equilibrium problems, we took the third charge here because the two end charges are of same nature. So equilibrium point will be somewhere in the middle. Now on this third charge, I am assuming, let's say it is Q, and we balance force on Q. That's what we did in the first example. That's what we have written here again. And we already got the value of x, 12 by 5 in the first problem. So balancing equation on this third charge, balancing forces on this third charge gives us the position, and we got the position here. Now the second step, to find the magnitude of the third charge, we have to write force balance on any one of the other two charges. So the other two charges, either 4q or 9q, we have to write force balance on any of these two charges, any one of these two charges. Here let's say I am assuming 4q, we have to do force balance on 4q. So in that case, let's see it logically first. This 9q charge will try to repel it because they are of same nature. So 9q will repel 4q, the force will be towards left. To balance it, the small q must apply a force towards right. Small q must attract the 4q then, because if the force between 4q and q will be attractive in nature, then only small q can apply right side force. If q, the small q, attracts 4q, then only the force will be towards right. This gives us this small q must be negative sign. The small q sign must be negative. Again, the 9q is trying to push it, right? Because both are of same nature. That's why the force on 4q will be repelling nature. So 4q on 4q, the force due to 9q is towards left. To balance it, force due to q must be towards right. That means small q must attract 4q. Hence, small q sign will be negative. This gives us part of the magnitude. Now, what is the number part? We got the sign. So let's write the force balance equation on 4q. So k 9q into 4q by L square, because the distance between them is L, right? So I am writing the force between 4q and 9q, that is k 9q and 4q by L square. And force between these two charges 4q and q will be k q 4q by x square, and x value we have already got, it is 12 by 5, and we put the value here. So if we put the value of x square, straightforward we get the value of q as 36 by 25 times capital Q. and the sign is negative, hence the magnitude of q I can write as minus of 36 by 25 q, and this is the answer. Now let's look at this example. Now this example is exactly same as the previous example. Here also we have two charges q1 q2 and we need to place a third charge somewhere, but here the charges q1 and q2, their position vectors are given as r1 and r2. These r1 and r2 are in vector format. So the position vectors of the first two charges we know, and it is asking find the negative charge. So it is already saying that the third charge q3 will be negative. Find the negative charge and the position vector r3 of the point where this q3 should be placed. So here the question is exactly same as the previous one, but we need to use the vector form of Coulomb's law. So let's do the same thing. So when we have and look at the final question, it is asking all three should be in equilibrium. So when all three should be in equilibrium, our concept says first we need to do the force balance on the third charge. So we are doing first force balance on the third charge, that will give us the position. Then the next step will be to do force balance on any of the two end charges, either q1 or q2. We write force balance on any one of them, and that will give us the magnitude of the third charge, right? Now let's do it. So first we are writing net force on q3 to be 0. Third charge we are trying to balance it, the net force on the third charge. So we are writing the force in vector form. See, if I write force on 1 due to 2, then it will be the magnitude of the force k q1 q2 by r square, but the direction will be r of 1 with respect to 2, right? So that's what we have written here. But look, they have already told us the magnitude, the q3 value will have negative sign. They have told us already. So if I would have written it, normally I would have written it k q1 q3 by r3 minus r1 vectors magnitude into r3 minus r1 vector. This is how I should have written it. But I already know q3 is of negative sign. So that minus sign I am multiplying inside the bracket and I am making it r1 minus r3 vector. And anyway we are taking the magnitude here, the sequence does not matter as if it is r1 minus r3 or r3 minus r1, it doesn't really matter here. So the same thing I have written for the second part of the equation as well. So force on q3 due to q1 is this much, that is k q1 q3 by r1 minus r3 vector whole to the power 3. This is the magnitude part and this is the vector part, the direction, r1 vector minus r3 vector. Similarly here also I have written force on q3 due to q2. So it should be k q2 q3 by r3 minus r2 vector mod to the power 3 into r3 vector minus r2 vector. Again it should be this way, but I know q3 is negative, that minus sign I am multiplying inside the bracket and I am writing r2 minus r3 directly. Now after writing this, I see that as the two forces are balancing each other, so the force on q3 due to q1 and force on q3 due to q2, they are exactly opposite to each other, so their line of action is same. Anyway Coulomb's force is a central force, so here the force will be along the line joining the two charges. As we are keeping q3 in the middle, both the force must be along same line, but they are of opposite direction. So if we write the direction vector, the unit vectors, then the unit vector must be opposite to each other, and that's what we are seeing here. So this vector here r1 minus r3 by r1 minus r3 magnitude, this gives us the unit vector towards q1. This gives us the unit vector towards q3. That's why we have put the minus sign. They are of opposite direction. Their unit vectors must be, unit vector means their magnitude will be 1 anyway, but their direction should be opposite. That's why we have put the minus sign here. Now from this, look, we can check here. Here r1 minus r3 to the power 3 is there. So if we decrease the power by 1, I am keeping it square, and one of the R1 minus R3 mod I am taking it here. So this term and this term on the second part, they will be same, right? So that's why these two term can cancel out. From the remaining part, k and q3 I am taking common. So I am getting k, q3 taking common, r1 minus r3 vector by r1 minus r3 into remaining terms q1 by r1 minus r3 square minus q2 by r2 minus r3 square, and this term is same on both sides, so I am taking it common and dividing it on the right side. 0 by that much will still be 0. Now further moving on, see, the bracketed part must be 0 because we are given that this term must be 0. So that means these two terms should be equal to each other. That's what we are trying to say here. These two terms are equal to each other. So I am equating them and taking root over. So if I take root over, this side becomes, this is q1 root q1 by r1 vector minus r3 vector equals to, this is root q2 by r2 vector minus r3 vector, but there should be a plus or minus sign here. That's what we have written here after doing cross multiplication. So if we solve it, root q1 minus root q1 into r2 minus r3 and root q2 into r1 minus r3. If we solve it, then taking positive sign we get this much value, and taking negative sign with the equation we get this much value. So there are two positions of R3 again. This was the similar case in our previous questions as well. We were getting two positions, two values of x in those equations. So here why are we getting two values? See, we are writing the equations, then the net force is 0. But when mathematically we are trying to find it, the two forces magnitude are equal for two different values, but their directions are opposite to each other for a specific value. Now here this will not be the answer. Why? Because this position vector R3 will lie outside the two charges. We already know that if the two end charges here Q1 and Q2, the two end charges are of same nature, so in that case this R3 vector should lie somewhere in middle, right? So that's why this answer is not possible. This answer is an extrapolated point. Extrapolated point means, let's say here is our q1 and here is our q2 and this is the line joining them, then this r3 vector lies somewhere on the outside. It is along the line joining but somewhere on the outside, either on the left side or on the right side. It is an extrapolated point. Now how do you know, how do you see the equation and know that it is an extrapolated point? Let's see it vectorially. Here I have given this is R1 vector and here is Q1 present. I am redrawing this diagram here. Right, let's try to understand. And this is R2 vector. This is Q2 point. So our expression says root q1 times r2, means we are multiplying a number in r2 vector. That means r2 vector's magnitude I am trying to increase. Similarly, here I am also multiplying a number with r1. So I am trying to increase the magnitude of r1 vector as well. But there is a minus sign. So with this, I am trying to add opposite of this r1 vector. So my r2 vector already is given like this, and I am multiplying root q1 times. So r2 vector's magnitude should increase. It should be along the same line. It should be along the same line, but the length should be more. Now, if I add opposite of R1, opposite of R1 means it should be somewhat like this, but again it is multiplied with root q2 times. So again the magnitude will be further increased. So our equilibrium point should lie somewhere joining the line q1 q2, right? So if I extend the line joining q1 q2 and I extend this yellow line which shows us this value. So look, they try to intersect somewhere outside. Here is my q1 point, here is my q2 point, and the intersection of the vector format here, if I try to draw the numerator part vectorially, diagrammatically I want to see it. So in that case I see it intersects this line somewhere on the outside. That's why we get to know that this R3 point shows somewhere outside the line joining q1 and q2. That's why this cannot be the answer. So our answer will be, by taking negative sign here, the answer I am getting here, this one shows the interpolated point, means somewhere in the middle, in between the two charges. Here also we can check the same thing by drawing the vector here. The point will be somewhere in the middle, and this point will be our answer. This gives us the position. Now, how to get the magnitude of Q3? To get magnitude, we need to write the force balance equation on any of the end charges, right? Let's do the same. Here we are writing, for magnitude of Q3, we are writing force balance on Q1. So I am choosing Q1, and on Q1 I need to write the force balance. So again I am doing the same thing. On Q1, force due to Q2 I am writing, and force due to Q3 I am writing. These two terms we are writing, and the net force should be 0. We are doing the process exactly same as the previous process. So from here, the Q3 term, again by equating the unit vectors, this part I can take common and cancel, divide on the other side. So Q3, from this expression, Q3 value on simplifying, I get as this much. Look at this expression, here there is a R3 term which should have been unknown, but after writing the force balance on Q3, I already got R3 value. So if I replace this Q3 value here, see, here we are replacing the R3 value, we are replacing in this equation. So after replacing and simplifying, we get the magnitude of Q3 as this much. But while writing this, we have not taken the magnitude of the sign of Q3. Sign of Q3 they have given us negative, but while writing this, we have not taken the sign of Q3, because see, force on Q1 I am writing, and here I have written R1 minus R3. Again force on Q1, it is R1 minus R2. If I would have taken the sign of Q3, then the minus sign should have come here, and it would have been R3 minus R1 then, because force on 1 due to 3 we are writing. So in that case, R1 minus R3 should have been written, and that much we have already written here. That means I have not taken the sign of Q3 here. That's what I have mentioned also. Here we have not presumed the sign of Q3 before. So from logic, we only got the magnitude of Q3 as this much by simplifying, and we put the minus sign with this Q3. After putting the minus sign, this gives us the entire expression, which is the magnitude of Q3, minus of Q1 Q2 by root Q1 plus root Q2 whole square.